Hello. This presentation will propose how to advance capsule endoscopy battery technology by applying advanced manufacturing methods. Endoscopies are medical procedures where a long, thin tube affixed with a camera called an endoscope is inserted into a channel within the body. Endoscopies offer medical professionals vital insights during patient diagnosis and condition monitoring, but are invasive procedures and can result in patient discomfort. Ingestible medical capsules, as an alternative, has gained traction. A diagram of a typical capsule is pictured. They have become common practice and offer many advantages, including minimal patient discomfort. Relying on passive movement of the capsule introduces challenges, such as risk of retention, the capsule could get stuck inside the tract, and diagnostic uncertainty, the inability to maneuver the capsule to view suspicious lesions may warrant an additional examination using a traditional endoscope. The next generation of capsules will utilize active locomotion. Some examples pictured. Active locomotion will allow medical professionals to control and navigate the capsules as they pass through the body, drastically reducing the risk of retention and reducing uncertainties in observation. However, introducing active locomotion demands a power capacity exceeding 400 milliwatts. The current 2 silver oxide coin battery design becomes a bottleneck for improved applications of the capsules. Silver oxide coin batteries are manufactured using a standard process. Many of the steps require unique machines. There are 2 major sections of production: electrode sheet preparation, where the anode and cathode are prepared, and cell assembly, where the final cell is made. Using the electrode sheets produced in the left process, the steps on the right will produce the final cell battery. The existing battery is sized to fit within the capsule casing, which is limited to a maximum of 1 centimeter in diameter and 3 centimeters in length. The power storage restriction heavily limits the viability of many of the innovative capsule designs. Thus, it is necessary to improve the capsule power source through advanced manufacturing of an improved microbattery outfit. A new power storage method must meet the following requirements: produce greater than 400 milliwatts, not exceed a 1 centimeter in diameter and 3 centimeters in length, last for at least 8 hours to compete with the current silver oxide batteries, and due to being inside of a human body, the power source must be approved by the necessary agencies for use in medical devices.
In order to move forward with endoscopic capsule locomotion, the solution that is being proposed is one that includes a power unit of high-powered lithium-ion microbatteries. These will be used to replace the 2 silver oxide coin cell batteries that are currently used in the industry capsules. The silver oxide coin batteries are only able to generate 20 milliwatts of power, which is insufficient for controlled locomotion of future capsules. The proposed microbattery boasts a much higher power density while remaining comparable in size to the silver oxide batteries. This increase in power will be sufficient to run the locomotion mechanisms and propel the capsule through the esophageal and intestinal tract. The microbatteries are produced using nanomanufacturing technologies to precisely control the particle structure. Much like the silver oxide batteries, there are 2 different processes required to produce the battery structure: nickel scaffolding fabrication and electrode deposition. The first process is creating the nickel scaffolding. Interdigitated gold templates were produced by sputtering an 8 nanometer chromium layer topped with 70 nanometers of gold onto a glass slide. The gold and chromium layers were etched to produce the contact pads for the interdigitated anode and cathode cells. The glass slide with the gold template is cut into smaller substrates and prepared for polystyrene opal growth. The substrates are positioned vertically in a colloid solution and then placed on a hot plate to dry. The substrates are sintered and then the nickel is electrodeposited. The polystyrene is then removed by immersing the substrate in tetrahydrofuran followed by oxygen plasma etching. With the nickel scaffolding then built, the next process is to add the anode and cathode materials. First, a nickel tin alloy is electrodeposited onto the scaffold to produce the anode. Manganese oxide is electrodeposited onto the scaffold to produce the cathode. Then the substrate is immersed in molten lithium salts to form a lithiated manganese oxide. The figure included depicts the manufacturing process of producing the polystyrene structure in which the nickel is deposited, and then the polystyrene is removed in order for the anode and cathode to be deposited. This advanced manufacturing nanoscale process is more complicated and takes longer than silver oxide process, but it will produce a superior battery. One key factor is that silver oxide batteries are only batteries that have been approved so far for clinical use. This would mean that the new battery would need to be tested and approved before it could be used in endoscopic capsules. The design is expected to remain a size that will be able to safely pass through the esophageal and intestinal tract, as well as power the endoscope and a propulsion mechanism for a period of at least 8 hours. This new design should also reduce the inherent risk of retention because of the locomotion capability. It will be able to dislodge itself better than the previous passive movement design by the use of legs or vibrations. However, there are limitations to the design that include further costs due to the complexity of lithium-ion microbattery production. Approval and testing limitations will be covered in future work.
Lithium-ion microbatteries perform relatively well compared to other power sources with respect to power density. However, they have average energy densities, which can even be considered low in some cases. This means they can provide very large amounts of energy for short periods of time while still keeping a decent discharge time. Moreover, experiments have been done using different C rates which govern the charge and discharge time. All C rates show promise, which indicates that the batteries can be tailored based on the required operating time and available voltages. The figure shown on the slide shows different C rates for the battery, which are labeled A to H, and shows how they compare against different power sources. To summarize, lithium-ion microbatteries come with positives as well as some drawbacks. The most important advantage, which outweighs any of the drawbacks, is the extremely high power densities these batteries can reach. One important drawback worth mentioning is the high risk associated with the rare occurrence of material leakage from the battery, which can be toxic to humans. Other drawbacks include the high cost associated with manufacturing, as well as the amount of time and money that need to be invested before these batteries can be used for the desired application.
Substituting the silver oxide for a lithium-ion battery, our design introduces a number of areas for future work, including effects on the capsule casing material and design, and achievement of medical licensing for both the medical device and approval of use of the battery in the medical device. We will provide further details on each of these areas in the coming slide. Due to the supplementation of the silver oxide battery with the lithium-ion microbattery, there is an increased risk of patient toxicity in the event that the battery were to rupture. The current capsule casing is made out of a rigid polymer, which is sealed shut with a biocompatible epoxy. One key area of future work would be to test the lithium-ion battery chemicals against the integrity of the current isoplast casing and to determine the effects. A leak-proof casing design is a huge area for future examination, and an alternative biocompatible casing material may need to be examined for future use. In order to use our design as a medical device in Canada, it must obtain a license through the Government of Canada. Medical devices are regulated by the Medical Device Bureau of the TDP, and previously capsule endoscopies have been issued a Class 2, which is low-risk medical license. In order to commercially produce this improved endoscopy design, a medical license must be obtained. Approval of the battery for clinical use is another area of future work. The battery specifically must obtain a separate medical licensing in order to be used in a medical device in Canada. In conclusion, although commercial capsules have been in production for several years now, the current applicability of the devices is limited by the passive movement through the GI tract, which introduces diagnostic uncertainty and the risk of retention. Implementation of active locomotion through the GI tract is constrained by the onboard battery power of the current battery outfit for the capsules. By supplementing the silver oxide batteries with a power-dense lithium-ion microbattery, this power constraint can be eliminated, vastly improving the capabilities of the wireless endoscopy capsules. Although promising, there is still work to be done in this field, including the examination of the capsule casing, as well as the licensing requirements related to the battery supplementation and device approval. Thank you.